different technology, and it has other benefits like investigation of what material used, what kind of coating, and how it is manufactured. So in re-engineering, so we start with the selection of existing component. Then we try to optimize something. It might be the lightweighting point of view. It might be from the topology optimization point of view or the performance point of view. So when I say optimization, it cannot be only, what we do stress-based optimization using, any of the tool. Even we have Apex Generative Designer, Nastron or any other solution. So it is only stress-based optimization. So optimization cannot be only stress-based. So it has to be from thermal point of view, frequency and other stuff as well. But we can do that as well. So as I said, before we jump, so there is something called part identification. It is not that every part can be replaced with the 3D printing technology. So now we have to identify the part which is more realistic for a 3D printing. Otherwise, my whole exercise or my whole effort will go wrong. So now in fact, we have developed one software for that. So where we upload the component and define this is my component and material. So what it will do, it will search for a similar material available with the 3D printing, because 3D printing has limited material as of now. You take polymer or metal. Let's take example of metal which we have done for one of the university race car recently. So it was printed with aluminum, but in aluminum there are only two grades available for 3D printing. That is of 10 mg and the second is of lower aluminum with some alloy material. So now if I replace the existing material with the 3D printed material, so what will be the difference in material property? So if I come to know that, rest I can easily calculate. If I am reducing my yield, so what will be my fatigue life, or what will be the performance of the 3D printed material? So this is very critical. In fact, we have limited resources or knowledge available on 3D printing. So it is very hard to somebody to directly say yes, this part can be easily replaced with the 3D printing technology. The other part is cost. So as we all know, cost competitive market. So how do we justify the cost? Only way to justify the cost, so we have to make some improvement on the performance, or we might be addressing the logistics related issue or any other challenges, so that it is easy for us to justify that this part can be replaced with the 3D printed component. Recently we have done one with one of the machine bracket, which I have in the coming slide. So it is expensive than the conventional, but lot of logistics related can be addressed. Same with the many defense project we work with. So many of the components still we import from France or from the OEM. So all of this can be instead of waiting for a logistics time, so we can 3D print. The another one, still we are dependent on China for a casting. So where we want to get a casted component or the die. So it takes at least 3 to 9 months to get the casted component or the die or mold. So instead of that, we can 3D print that, and we can bring that 6 months to 6 weeks or 3 weeks. So that is a major advantage. For that, we should have a knowledge on identifying the part, and not only identifying and justifying from the cost and performance point of view. So then comes how do we print? So printing itself, you see a lot of paper on printing with a different direction. Each direction printing strategy will give a different properties. So selection of printing strategy is another key challenge. So in fact, what we can do is we can digitally validate that, or if I have some data, I can put it into software and understand. So once I finalize that, then I go for a DFAM. So this can be interchangeable. I'll identify the part. If there is a room for a light weighting, I will go with the DFAM first. DFAM, design for additive manufacturing. So I do the light weighting and topology optimization. Then I prepare the file for printing. So before print, whether it is in a metal or polymer, so we go for a we call it as a manufacturing feasibility study. So we can use different software or any algorithm any algorithm available. So then we can take this data into that, and we understand whether it is printable or not. So then, no, again, so we are talking about a different set of manufacturing. So 3D printing itself has, a 6 to 7 different technology, like it can be FDM, DED or LPBF or other processes. We can check with the different set of processes. Then comes the quality inspection. So if it is a reverse engineering, I will start from here. So quality inspection either can be CMM or a regular 3D scanner. So why do we do this? To understand that as printed, it is in line with as designed. So there is no deviation or distortion. So that is the overall idea. So this is a complete 360-degree cycle of 3D printing. So as I said, you can start from here or you can start from the part identification. So most of this can be supported by the software tools, but still again it required a lot of data. When I say cost estimation, we have to give what is the powder cost. So in which machine we are going to print, how many parts we are going to print. So there are a lot of manual work and understanding has to be done before we use this software tools. Yeah, so if I put different set of process or software together, so this is how it looks. So we start with part identification, then comes the costing. So before I commit or before I start any project, so first I will identify the part, then I will get the approximate cost, so that here only I am sure that whether my work is going to be justified from technical and commercial point of view. Then we look about alternate material. Not every material can be 3D printed, and we have limitation as we discussed. Then we talk about if there is a room. So before we go into DFAM, so we should know the complete multi-body dynamics of a system. So I will give one example of race car wheel hub. So wheel hub is a very critical. It is not because all the loads coming over there, and if I replace the wheel hub with a 3D printed wheel hub, so most of the student race car, so you have a wheel hub, and every university is trying to do this. When I replace the conventional wheel hub with 3D printed wheel hub, you have to test with at least 6 different conditions. While accelerating the car, you will have a different load. While curving, you have a different load. While braking, you have a different load. Like that, there will be 6 scenarios. All has to be passed by 3D printed component. So we need a better understanding of loading condition. So once we know that, then we can talk about lightweighting and other stuff. So then we go for a performance. As I said, we have to test with different loading condition. Once I have this, then I go for a data preparation, feasibility study. Then also we can plan for post processing in the sense. So after printing, if does it require any coating. So as you know, the printing, some of the process may not give the required surface finish. Then we have to go for a machining, polishing and other things. So those things can be defined over here only. Then we manufacture and inspect. We always say that printing is a last stage. So before that we have to thoroughly calculate the fatigue life, durability, then material related property and manufacturing feasibility and the cost. So if I have all the report ready, then only we go for a printing. So this has been workflow for the OEM. So as we always look this workflow as a master chart, but if you are a service bureau, you might not be looking at all of this process. Or if I am a researcher, I am not really bothered about the design and other stuff. So my area would be more of understanding the build related and performance. So my area of understanding might be the post machining and coating. So like that we can pick. So as I said, we have in fact at Hexagon we have one we look for a OEM. So in fact I work with GE, Honeywell, Eaton in India. Then we have research and academic and the service bureau. So each one the focus is different, but if we are a OEM or in fact we have to justify, then we have to portion of our end-to-end 3D printing technology. Yeah. So what we do, this is just to give an overview of Hexagon. So Hexagon is a Swedish company. So we are the autonomous driving. So manufacturing intelligence, this is what I represent. So when I say manufacturing intelligence, it's more of focused on industry 4.0 and how do we integrate between software and hardware. So otherwise, our focus is more on geospatial and hexagon, and we control the UP dial 112. All of this project were done with us. In fact, we work very closely with ISRO for geospatial and other stuff. So this is what the portfolio, but I represent as a engineer, so our major focus is on manufacturing intelligence. So this is our presence. So you might have heard more when it comes to industry. So as I said, our presence is more in the industry and high precision manufacturing. So academic, yes. So we are pitching up now. So we have a couple of offers, e-learning and other stuff. So otherwise we are well known in the industry point of view. So this is what we do. So a lot of digital twin. If I talk about different brand, the MSC software is part of Hexagon. Then Leica camera, then Esprit. There are a lot of, at least we have 7 to 12 brands within Hexagon. So and we have our own drones and robotics, which we have integrate for the real-time application. So from the manufacturing point of view, so any questions? Okay. So from the manufacturing point of view, so what is important? The creating a digital twin. Nowadays we talk about digital twin of a any environment, or it can be digital twin in the sense replication of physical world in the digital, in the sense whatever happening on the, let's take example of a 3D printing machine. So we will be visualizing, or we will be replicating the same. The same time we can put some sensor and make it more realistic, condition monitoring. So when I get the data live, so it will become condition monitoring. First I will create a digital twin, in the sense I will create the same set of environment. Then I use couple of sensor to monitor how, let's take machining process. So what is my spindle speed? I can put one sensor and understand the rotation speed and make it visible in the software, so that it will become live monitoring, or the digital twin connected to the machine. So then we have other software where we can simulate and understand the material flow. We can understand the loading condition and other stuff. So then we can do conventional process as well, welding, joining, and effect of this process. So today we will be more focused on DFAM and additive manufacturing, and costing is another important factor. Even we say that 3D printing is pretty much adapted in healthcare and space and aerospace. So automotive, still we have a challenge because of the cost competitiveness. So R&D, yes, they do. In fact, we work with a Ford, even in Tata Motors in Pune. I was there last week to do a couple of new design 3D printing. So all of the design verification still with the machining or casting, because of the large volume and cost related aspect. But it is, presence is there, and looking 3D printing is a alternative solution, or it's a complementing. It's not going to replace any of the existing manufacturing processes. So why it is important? So we have been talking about the major pillar of industry revolution. So additive manufacturing is one of the pillar in the industry 4.0. We might have earned artificial intelligence, a lot of other trends, but additive manufacturing is one of the. So what we call it as cyber physics, in the sense how. So that is a major focus of industry 4.0. Yeah, sorry. So I think this you might have discussed. I was going through your course material. 3D printing. So many of student ask, sir, I'm planning to start my career in 3D printing. So how do you see from the job perspective? So we have shortage in skill, or the students are student with additive manufacturing skill. So there are many startups, they are looking for anybody passed out who is having 3D printing knowledge, at least to have a hands-on the machine and software, so that he can be directly employed. So those shortages there because the awareness of 3D printing is still not up to the level, especially for the current situation. So this is a scenario of how we started. So we started, in fact, when I was doing my engineering, it's more of a hand drawing. Then we moved to the CAD. So now we are moving to the more of a optimized or DFAM level of optimization. So we are starting with a generative design. So you may ask a question like, what is the difference between generative design and topology optimization? So topology optimization, when we use any software for a topology optimization, so it will be done with a given constraint. I have the existing part, so let's take this is my part. I have a loading condition. It will only optimize within this volume. So when I say generative design, so I can define any volume and it can come up with any shape. So there is no constraint on the volume and there is no limitation on the volume when I say generative design. That's why we call it as it can generate its own design. So it can come up with the unique shapes for 3D printing. And the advantage of 3D printing, the complexity comes for free. So if some design is not complex, better not to go for 3D printing because it can be easily manufactured by conventional way. When design complexity comes, so 3D printing can be easily justified. So this is one of the example where we have used topology optimization. So we have done with tree root structure, then lattice. So this is done with Apex generative design tool. So where we have integrated this structure together so that there is no need of support structure. So you may ask, what is AI based? So we have been climbing AI based optimization, AI based optimization. It is an algorithm written. So in this case, we have written an algorithm saying that any surface less than 45 degree need to be avoided, so that my support structure can be avoided during printing. Then anything less than 0.5 mm is difficult for aluminum material. Then I will write an algorithm saying that don't optimize any wall or any part less than 0.5 degree. So then it will use the algorithm and it will scan throughout and it will optimize in such a way that my wall thickness is always higher than 0.5. So that if you look at if I have to do it manually, how much effort I have to do, I have to manually inspect, and inspecting this kind of structure is impossible. So now we go for a AI based, or we call it as narrow AI tools, where we can give this condition so that it condition will be applied along with the regular topology optimization. So that is what we have done. What are the advantages? I think you know that freedom to design, then we get very strong and lightweighted. So we are not compromising on the strength. At the same time, it is a lightweighted structure. So customized. So when it comes to the medical, so we have done one with Manipal Hospital in Bangalore and one in Sanchiti Hospital in Pune. So when it comes to implant, so every human being is different. So we need a customized implant. For that, this is the best technology where we can print the implant. We call it as patient-specific implant. So which suits for him. So not something suits for him. We try to force fit. Then patient will feel the pain. So to avoid that, we go with more customized. So now fashion industry also looking towards additive manufacturing. Speed to market. So as I said, lot of logistics related issues. So if I am importing couple of component outside India, then it can be easily replaced with 3D printing. That cost can be easily justified. So that's the advantage. So this is another example of satellite launching pad. where we have optimized and we could able to not only reduce the weight, so we were able to, improve the stiffness, also the stress distribution. So we cannot make stress as a zero. The only things we can take care, so it is distributed, not focused at a particular location which leads to failure. Instead of that, it will be distributed throughout the component, so it is taken care by the strength. Then when we talk about the customized, so this is one of the customized bicycle, you will get it. This is a folding bicycle. If you go to their website, so you can choose the color, you can choose the different types of frame. So based on the passenger weight, they can change the frame. So all of this, because this is a folding bicycle, they will carry. So it has to be as light as it possible. So these are the things which we are doing with 3D printing. And as I said, if it is not complex, then it's not suitable for 3D printing, because it cannot justify that technology and the cost we spend. So pain point. So it is always hard to justify from the cost point of view. As I said, when it comes to the performance improvement, so it is easily justified the cost. So otherwise, we are always questioned, why do you want to go with expensive processor? A lot of questions will be raised on the performance point of view. So we have to spend a lot of time on proving that yes, it can perform better, and we don't have any standard as of now. So that is another things. So we always, what we do is we test the quality and we will put it into the system. So in fact, what we always say that we do the CT to understand the material strength and the internal dimension. So once we have the CT, so that is a qualification method we follow. So then, as I said, the whatever points we have discussed, so this is already available. So I was mentioning missing expertise. So that has been still, the concern for us. So we have a lot of resource gap between what industry is looking and the people trained on the field of additive manufacturing. So this is one example, so which we have recently done for one customer, and this is just to say that maybe I'll ask you. So how many of you think that yes, this is a good optimized design? So don't raise your hand. So that's also fine. So what we are trying to say here, see, as I said, when the design is very simple, when it can be conventionally manufactured, so it makes no sense to put all our effort and come up with a topology optimized design. So this is not the right design, because the printing time and the complexity is higher than what it can be done conventionally. So this is just to show that when we cannot justify from the design point of view, so it is not recommended to use the 3D printing technique. So also we have to do the part integration. So instead of having single part, we can integrate 3-4 part and get it printed. So that is another advantage which we can get from the 3D printing. So now let's, any questions so far? No? Okay. Yeah. So cost is dependent on 3 factors. One is volume, as you said, then the material we use, and MHR, in the sense machine hourly running rate. So these are the 3 factors. So and it changes from machine to machine, regional wise. So if I get material from the local supplier or the OEM, the cost will be different.
Like if a client comes with you as 2D design or a sketchy done, you will convert it into 3D first, then you will take cost, and then you will do printing.
Yes. So first we have to get a 3D model, because we need a volume. So then we take that into the software, or even we can calculate the volume. Then what is the material required to print that component? Then what will be the material cost and machine cost? So machine cost includes the energy consumption and labor cost and other things. So that is how it is calculated. You can do it in Simufact as well. It has one module called cost estimation. So it can do that also. You can have a local cost also. So top of it, if you have post-processing and material loss, you can give that percentage as. It will predict very accurately. So that we can do. Yes. Any other question?
This STL file is there, sir?
Any native file format. You are asking.
STL file is there?
STL. So you can use STL, step, parasolid, anything will be supported. So there is no constraint on the file format.
Not mandatory.
Any file. It's an open tool kind of thing. So any native CAD file can be imported. I may have one slide. I'll see if I have that slide. Okay. So this is, we call it as the generative design cycle. So when I say topology optimization or DFAM, so before that we start with the initial understanding of the design and non-design space, in the sense where are the area where I am not allowed to remove any material, because it might be fitting into the another body, or we may have to integrate with the main system, or this might be the load bearing areas where we are not allowed to remove the material. Also, not only that surface, the surface surrounding 5 mm, 10 mm, we should not do any optimization. So that is my, the first, before we import any geometry. And then, so intelligent smoothing. So all of this is done with a narrow AI tool. Intelligent smoothing in the sense, now let's say we have given the problem statement to 5 students. So each student will have a different meshing condition, and he will put the same load, but result will be different. So instead of that, the software will come up with its own meshing and geometry cleaning, so that whenever you apply the same load, so 5 out of 5 students should get the same fatigue life. It should not vary, because I am not varying the loading condition, I am not varying the geometry, but still my result will vary because of the mesh. To avoid that, we have introduced this intelligent smoothing. So what it will do, there will be predefined algorithm. So the sharp corner has to be, it's more like a thumb rule. Wherever I have a sharp corner, it should have at least 3 mesh element, if it is a tet element. So in the flat surface, it can go till the ratio of 1:3. So that my meshing in line with the basic principle of how much element has to be there in the sharp corner, what should be the element size in the middle of the component. So all of this will be taken care. Now if you go for a the design candidate, and you want to export and see the manufacturing feasibility or the durability, you will have the unique results. So you will have the unique result if you include manufacturing feasibility, otherwise it will be the same. So it is not different for each one. So now we talk about how do we print. So now we understand the loading, meshing and geometry cleaning, then the topology optimization, then this talks about durability and the printability. It is not always true that any design can be easily 3D printable. So it will have its own challenges when we have a internal cooling channel, the wall thickness which is less than particular dimension with respect to the material. There might be buckling related challenges. So I may provide, if you look at closely, this is a support structure. If there is an internal cooling channel, if I generate a support, how do we remove it after printing? So there will be challenges from the manufacturing point of view as well. So that can be taken care by understanding, or just we always say that first run a thermomechanical simulation to understand the manufacturing feasibility, then we can go for a final design validation. Manufacturing feasibility itself, we have a lot of parameters to consider. What is your printing strategy, what is the material, and what kind of support structure you use, whether it is a solid or cone type. So there are a lot of other parameters which can influence the part distortion and residual stresses. So this performance of the part. So this is what we have to do when it comes to the optimization. Example of as I was in the previous discussion. So this one of the wheel hub which we have printed locally. At least I have 6 to 7. So this could be one of the interesting component. If you have a, I'm sure every university has one, the student formula car. So now it's a challenge that the lighter the wheel, you will have better cornering efficiency. And the mileage, but mileage we are not focusing. So now we have better handling and cornering efficiency. So we are trying to optimize that wheel hub, and we are trying to replace with a 3D printed one, so that we will have a better performance of our race car. So this is one. So student can take up and optimization challenge. So we can work on that. So as I said, when we jump into it, so we have to start with multi-body dynamics to understand what is the vehicle is designed for, what is the weight coming to the each, the wheel joints, and this wheel hub same time it is critical. It is connected to the suspension, it is connected to the brake pad, and it is connected to the wheel, and a whole vehicle load is coming to this component. If it fails, the vehicle will stop. So we have to take both the loading condition and DFAM into the account, and we can do further optimization. So this just to show that when we use tool or when we don't use AI based tool, so how much effort I am putting manually. So if you look at one on the existing software, so now you have to run with 3 to 4 different software, one for topology optimization, one for meshing, then one for design optimization, manufacturing feasibility, all of this. So by the time you run through the different software, each time you have to save the result, export and import. Sometimes it will not be compatible, file format will not be compatible, then you will have a lot of data loss. But all of this can be eliminated using the AI based tool. It's a open AI in the sense, when I say Apex, limited to the only lattice, or any honeycomb structure. You can come up with your own structure, or you can come up with any unit cell. We call it as a unit cell. I have one unit cell per volume, then it will be replicated throughout the body. So you can come up with any unit cell. So that the manual effort we put on the meshing, geometry cleaning can be eliminated, so that I save at least 80% of activities, which is of geometry cleaning and other stuff. So that's what it says. So 6 days. So that we should focus more on the engineering stuff than non-engineering stuff. So this is how it works. So mesh generation is automatic, and then we have to only define the constraint and optimization. So what is my optimization goal? So whether I am doing it for a metal, polymer, or what kind of result I am expecting from this, then it will do the smoothing and the repair automatically. Then with one click, export the STL file. Not only that, somebody can ask me a question, STL is a non-editable file format. Editable file format. Then you can generate a NURBS, in the sense you can mesh it and make it as editable. So that is another advantage. So any editable, you can convert it into editable file format. So this is a automation or narrow AI algorithm written. So why we use or not of non-engineering stuff, we will give it a job. So this is what we have a lot of automation in the topology optimization. Trying to understand what do you mean by optimization. So what it does, how does any optimization tool, it is not specific to one tool, so it's about technology. So what it will do is, currently I have a component, can you see here, I have a component. For any optimization, I need one component, one force acting direction, or one loading condition, and one fixed point, or you can give fixation as another geometry. or you can fix a body. So it will apply the load on the given component, then it will understand how the stress distributed within the volume. So every material has its own UTS. So it will compare the stress with UTS in each element. So wherever it is less than UTS, it will remove or delete that element. So that what it will become lighter. Can you see? So these are the area where the stress is less than the UTS. So it removed. So again the same set of load will be applied. Then further iteration it will remove further material. This is clear? Any doubts? So this is how any stress based optimization tool works. So in optimization there are many. So what we have been discussing is only about structural and stress. There is a thermal optimization, there is a frequency optimization, then optimization can be co-simulation using multiple optimization in a single body. So all of this were feasible, but we start with a stress based optimization because this is critical from the load carrying and fatigue point of view. So thermal and other things can be optimized later. So now the same type of loading condition will be applied to the larger component. So this is I chosen just to explain that how this optimization works. So and I can pick internal iterations as well. And if you compare this with the original, you will have a lot of weight savings in it. So it means to say that this material is enough to handle this much force. So that is what it is justifying. So how does this complete optimization or DFAM funnel works? So we have seen stress based optimization. First it will check the stress throughout the component and it will subtract or add the material. Then it calculates the weight, how much weight has been optimized from my original design to the final design. Then design complexity, because we have, as I said, we have written lot of algorithms saying that you don't optimize less than 45 degree, reduce the wall thickness, all of this will be checked. Then the manufacturability. So when it comes to the fashion industry, they are not much worried about fatigue, but they are more interested in the unique design they want to get out of 3D printing. So they want to have a unique design or unique looking design. That can be also one of the conditions. So these are the conditions during manufacturing process. So that any design I have, so it will satisfy all of this condition and it will come up as a final component. So top of it, if you want to add your other aspects also, you can add it. So you may say that you want to optimize for only one material. You may optimize for cost also, you can add it here. So this is a complete DFAM workflow. Start with the stress to the manufacturability. So these are the different designs. So you might have already seen how do we use the lattice, tree root structure, honeycomb, and the whatever you see on the right, all of this will be done automatically using the algorithm. The smoothing, the geometry cleaning, then converting STL to the step file. So all of this will be done by the software. So you have to only spend time over here. So rest of the things will be taken care by the software. So this is a kind of advancement we are seeing now. We talk about meshless optimization. So in fact here we know there is no manual meshing, but there is a meshing in the background which is done by the software. So then the automatic cleaning of the geometry. So now we spend only on the few clicks and we will be more interested in understanding the part performance than the geometry and other stuff.
But what about the dynamic loading? The optimization is done majorly on
Static, yes. So now what we do is, so once this is done, generally what we do is we start with the multi-body dynamics. We choose the maximum load in the each direction, so that we take it for optimization. So once we have this, the final shape, then we put it back into the multi-body dynamics. Yeah, it is a part. Yes. So as I said, MBD, frequency and thermal can be added. The first point, so what we try to make is we simplify the loadings, we take maximum in each direction, then we optimize it. Yeah. So this is another example of the same loading condition and I want to optimize for a minimum support structure. Let's say I know that I will print this part using 3D technology and I want to optimize, I want to print with no support. There are a lot of algorithms. So now you can see that you can make it as a no support algorithm active so that it will optimize in such a way that when you print it, you require very minimum support. So that your material wastage will come down, the powder cost will come down, other stuff will be done. So this can be done during design stage itself. See, during design stage itself, it is good to have the manufacturing principle during design stage. Otherwise, I go to manufacturing, fail and come back. So that approach will take very long time. So that manufacturing constraint is considered during design stage. So let's look at couple of case study. So this is just a comparative case study in the sense when we focus only on the topology optimization, we are limiting ourselves. When we are open for a generative design, when I say software that this is a loading condition and this is a material you come up with any design, then there is a more room for getting the very lightweighted design. So we always say that go with generative design, not with topology optimization. So this is one of the GE bracket challenge. So every student can take that component and try it. So these are the most of the example I show, it is implemented cases. None of this only the software cases. So we have optimized, printed and validated because we have that machine and the measurement equipment. So this is one of the TSAT satellite bracket where we had a major failure during the launching. There was a crack here. So what we have done is we understand the initial design, then what is the design and non-design space, load comings over there, so what are the different kind of loads, then we optimized and we could able to print. So during this we were able to save the weight by 50%. At the same time we are not compromising on the strength. So in fact we made it more stiffer and at the same time we focused on how the stress is getting distributed. So that is something we have to take care. So if that can be done, then the lot of failure related during the application can be avoided.
What is your validation involved?
It's a fatigue or life validation. In the sense, after how many cycles. The advantage of space and aerospace, there is not much fatigue. It's a one-time application. So we will just look for. But another limitation, they say that instead of UTS, you use the yield. We should not even go to the yield point, even though it is one-time application. So we limit to the yield and we put safety factor of 0.2 or 2.5 so that it is easy. So that's why I said AM is very much adopted in space, aerospace and medical. So this is another example I think now after post processing. So this is how the optimization runs. So automatic smoothing, understanding of stress, multi-body dynamics. So all of this will be done in the single platform. And it can be integrated with other tools as well. We always say that we won't compete with any of the software tool. So this result can be directly interpolated with LS Dyna, even though they are competitor. It can be interpreted with Nastron Solo 400, which is well known for a space application. So we have that integrations.
So this design is
Yes. So when it comes to the validation, that is a major input. It has to be taken care. Because first, so the optimization runs on the material characterization only. So when I start the optimization, I will give the CAD file, then I will define the material property, what is the yield strength, what is the Young's modulus and other stuff. So based on that only it does the optimization. So what we are missing here is manufacturing effect. So when I do the heat treatment, again property changes.
Strength and
That is the part identification software does. That will suggest alternate material. What it will do, when we select the part, no, it will compare the 10 different material which is equal, having equivalent properties.
But functional requirement, you define it, define the design as well as material.
Now, as you rightly mentioned, sir, what I am doing is, this is my initial condition is application requirement. Now it will screen select the material. That's what it does. But when I further optimize,
Selecting the you don't select the material.
okay,
This is your functionality only. At the end you tell that this is the material requirement is required for me.
okay,
Can I give the material or not is my problem.
okay. For that we have something is very much valid for a carbon fiber composite. Now I know the strength required. Now I can develop my own material with a different orientation. So that is more useful for a composite, as you rightly mentioned. So now I know the optimized geometry. So now I know what should be the material strength. Now I go back and develop my own material. That can be done. But it is easy for a composite and other things. But in metal, it is very hard to come up with my own material grade. Because recently we have done one with ISRO, printing aluminum alloy with ceramic. We were not able to even print 10 into 10 coupon. So we have tried all of this. The material requirement is it should have some thermal conductivity plus the aluminum property. Now when I try to develop a material development is a big, when it comes to metal, it is not that easy. No, we have done. For a composite, as you rightly mentioned, we have a tool. It will say that this is a required property. You choose any material or you develop your own material.
But
That.
in the manufacturing you are able to precisely, you are able to localizely, you are able to control the structure and graded properties are able to develop it. That is possible, okay?
So
You can design
for a 5 to 10%, by varying the printing strategy, we can vary. But that alloy will have its own properties. That is very difficult to.
In case you look at disk, okay, disk is you want equiax structure, blade you want syndication. This is possible. Okay?
Yeah,
That means okay, you are changing the entire range of properties and a given material.
so
By changing the structure, you are able to get that.
that comes in the post processing, as you mentioned.
Processing, you cannot do anything at all.
So we have done.
Doing one, you are doing.
Okay. But the base structure is very hard. That's what I also felt, because we have tried and failed many times. So that is easy. Software can throw anything. That is easy. It will tell that this is optimized structure. You come up with any material which will suit this requirement. But as I said,
For a given material, you are trying to optimize it.
no, even without material we can optimize, as you mentioned. So for this one, let's say I will not use any material. For this structure, for a 10 kg load is coming over here, you come up with any material which is having 320 MPa strength or yield. So now it is your choice to choose. So that is possible. We call it as, there is a good name, like grade down, material grading kind of things. They do this kind of project. The advantage is, so instead of going for a higher grade material, I will go for a lower grade material which will satisfy this condition. So that is a grade change project. This is called grade change project. So it will only tell the properties. I will choose the grade. So that can be done. So this is whatever we have discussed, lattice, all of this are predefined. So now I will inspired by nature, and this one of our customer who said, I don't want to use any existing optimization algorithm. I am inspired by this tree and I want to use this tree root structure for my design. So that is what we have done, and you know that there are many naturally inspired, honeycomb is one of the example of how we inspired by nature. Then we use that tree root structure. When we reverse it, so you don't require any support structure. You use this tree root structure so that part can be printed without any support. So there is an inspiration from nature. So then we have to use the same. So this is a conventional design. So now he said that no, I want to use, let's replace with this tree root structure so that I don't require any additional material. There is no printing related challenges. So it can be printed easily. So we have done all of this. So this can be done in Apex generative design. So this is a tree root which we used for 3D printing. So this design doesn't require any support because this itself acts like a support. So then lattice, not only lattice, varying lattice with solid plus lattice, tree root structure. So this is almost, saved 60 to 80% of the weight, and we have printed with aluminum material. So this is how we printed it. We printed and we give this to, we run one of the program called, our student will come and present in our user conference. We give this trophy to the best paper presented by the students. So this is how. So what we are trying to explain is, you need not to restrict yourself for only lattice or honeycomb or any other structure. So you can build your own unit cell and come up with a design. So this is the advantage of the software tools. We have seen this. So this is the one which we are discussing, sir. Now I scan the material. I know the loading condition. So it will tell what is the required property. Now you can develop your own material. Use a print a coupon. So this is pretty much possible in composite, because when you have a different carbon fiber orientation, you will have a different strength on that particular direction. So this can be done when we do. But for metal, still there are a lot of justification has to be provided. For composite, it's very easy. You know the unidirectional and bidirectional strength. You can develop your own composite material based on the application requirement. You know the passenger weight, you know the dimension. Now you develop your own composite material and give it to them. So that can be done easily. So this is how it was done. So material selection based on the application requirement. So this is pretty much can be possible. So this is what we are saying. When we are choosing, it is not only strength, the manufacturing process will come into picture, the part performance and the behavior. So all of this has to be taken into consideration. So then only we will be able to succeed. Otherwise, I can choose a material, but it is not, let's say copper, but not printable. So what do? Ceramic plus aluminum, not printable. I can address the application requirement, but printing or manufacturing is a challenge. In sometimes cost is a challenge. Like that, if we can integrate all of these three, we can come up with our own material grade. So this one you have seen, you will see in any of the high-end car. It might be Japanese or German. So this is called a light hinge project, which we have done for automotive automakers. So this is almost pretty much 70% 70% weight reduction. This is done with 316L material. So which was successfully done. You will see it in Japan and German cars. So this is wheel hub. So I have put this. So it start with topology optimization, manufacturability, and the multi-body dynamics. Otherwise, with topology optimization alone, I cannot say that yes, it will give the better fatigue or durability. I have to put under multi-body dynamics under different loading conditions. So we have used Adams, which is well known for multi-body dynamics, and we validated that. So this is a complete cycle. So start with the initial design, find out which are the design and non-design space. That is critical. Where are the area where I can remove the material, where are the area I am not allowed to remove the material. So then, we have to run through all of this process. Then we will be able to successfully replace conventional part with the 3D printed. So this has been done, I think, 5 years ago. Now, as I said, you will see every university is trying to do this. This is a workflow. It is not just one step. So we have to run with multiple DOE, in the sense selection of different orientation, printing strategy, different material. Then we have to compare all of this together, and we have to pick one of the best design out of it. So this is how it was optimized, and this part is already running from last 4 years. In fact, even in India, we have done multiple wheel hub optimization. Yeah. So if you want to really look at end-to-end process, so this is how it runs. So this is a complete workflow of DFAM, material selection, and 3D printing. So start with your initial drawing, convert it into 3D, do the optimization, check the performance, then manufacturing feasibility, prepare for a printing, print, measure, then quality inspection. If you require further correction, you can do it, then post-processing. So this is a complete cycle of implementing any 3D printing into the application.
Real quick, in this cycle, because I'm kind of having the same kind of question that at what point does material selection come in this flow?
Here, performance and the generative design. So now, sir mentioned, if I have just a property, I can choose 10 different material and see the performance. Geometry is fixed, but my material is not selected. So now the same geometry I will put aluminum and 316 and I will see the performance. So aluminum may run for a 10,000 cycle, steel may run for a 12,000 cycle. It is my call to say that what material to be used.
But isn't it also true that when you are optimizing the design,
Mm-hmm.
you cannot be agnostic to the material? Because some elements can be thicker or thinner depending on what material.
So initial material property we provide. So that is a base. So when it optimize,
Which means you have already chosen the material.
we have to choose some default value to start with.
But that is where my confusion lies.
Hmm.
Now, I mean, if you are picking a default value, it means you have picked the material in some way.
Hmm. So if you don't want, you can run only one step. See, these questions we have been working with industry.
Right.
This has already arrived. It's not something new for us.
Yeah.
Let's say you want to eliminate the material selection and you might be interested in new material development. I know the application condition. I will come up with my own material which is better than any material available in the market. That's what we did with the ISRO.
So no need to, we are not going to change the material, for example, okay?
Mhm.
But we can location specific manufacturer you can change it. So by modifying the things and optimize it, that is one of the another advantage of
Then we have to split the part, then give a different property to the different area. That can be done. You have to split the part and give a different property. That is the best way to do it. So that is feasible. Now, you want to be material agnostic or you want to run your design is finalized.
That means material is not design variable in this case. So is there a standard?
It is variable. It is not a standard. You can define anything. Let's say, there are two ways of looking at it. One, you define the material and run it. Other way, you understand the stress generated and develop the material to that level. Now, I don't know, maybe if I have a marker I can write and...
I think it is there, sir. Yes.
Okay.
The body.
Can I get a marker?
Given material optimizing the workplace.
There are two approaches. As I said, I'll explain This is okay. Here I have a cantilever beam. I'll so this is 10 kilonewton. So now what I will do is I will not define the material. What I am interested is when I apply 10 kilonewton, what is the stress generated over here? So let's say it will bend like this, and there might be more stress generated over here, which is of 320 MPa. So my target is I have to find out a material which is having yield strength of 320 MPa. So now we are choose. So now material is not selected. So I am coming up with a material requirement for a given application. My application is I have to design a structure which will stand for a 10 kilonewton. To stand 10 kilonewton, I need a property which is having 320 MPa of yield. So now my material requirement, I am deriving material requirement. So I will derive yield. So this is 320 MPa. Now the next, so I can do the further optimization, or I can consider the elongation limit. So that could be 20%. So I will consider the elongation limit, or I will call it as E or some factor. Then I will talk about so what will be the Young's modulus and Poisson's ratio, or I can just call it as epsilon. So now I have to choose for this condition. So let's say 0.3. So you can develop your own material which satisfies this condition. So any material I develop, it has to be 320 and above. If it is less than 320 MPa of yield, it will fail. It is not suitable for this application. So for this, what we do is,
But if you can change the stiffness in the range of design, even the lowest mathematical also can be fine.
yes, we have to give that as a variable.
The way you design the lattice structure, lowest mathematical also can able to meet the 320.
You can rerun the one more optimization cycle.
So little bit iterative in that.
It's an iterative method because we have to fix at least one variable and do the analysis. So with this, as I said, we included electric conductivity, other stuff. So that is what, as I said, one aluminum versus ceramic. So again, your variable can be thermal also. Now you say that I want to include frequency response also. Why only stress? So those things is iterative. We can do that iterative, and as I said, it's easy if it is a composite. It's a straightforward. Yeah.
Sir, you have quoted one example that Tata has used the optimization component.
Mhm.
May I know, can I get to know how many years they took to finalize the design, like start from the design to testing and application, real-time application they use the automotive component.
So as I said, it was used for prototyping. Not only that, even tire industry, the tire mold will be 3D printed, but actual production will be done with machined or casted component. I think the project duration was 4 months or something like that. So prototyping, you just want to prove the concept, or you may want to see the functionality and integration of the component. The same project. Okay.
He told that from real-time to design to testing component, it may take some 5 years or something to use it in real-time conditions.
Real time, they are not at even now they are not using any 3D printed. So
They are not ready to do. He told that there is some SLA something.
Yes,
like-
yes.
So they can get, so they can use it for the mass production component like that.
yes. So nowadays they need a new model in 2 years kind of things. They cannot spend much on R&D. So speed up all of this only they are going with prototyping with 3D printing technology. So actual production will have its own pro and cons. Yeah, so this is the overall cycle. So as I said, you can either start with reverse engineering and re-engineering, and it is not straightforward as you look in the screen. So you have n number of variables in each stage. Now we are talking about only material change. You can ask me, I will change my printing direction and the support structure. So it can also affect on our final part. So like that, we have a lot of variables throughout the cycle, which need to be taken care. The best way to, you have to digitally validate with all this variable and you print right at first time. So that's the overall idea here. And you have to use at least 5 to 6 different tools during this. So this is one of the example which is already done. One was designed for plastic, one is designed for aluminum. Yeah. So and this is a recent one of the cold plate used for electronics, which we have optimized with N topology, and we have understand the heat flow and other stuff. So far we have seen is more of stress-based optimization. This is thermal optimization, where we take the thermal and not only thermal, we can integrate the co-simulation. It is called a co-simulation. Structure, thermal, then fatigue. So all of this can be done on the single component. These are the other example of how we can optimize and further validate. So we always say that lattice looks good, the any unit cell looks good, but when it comes to the fatigue, those are the weak points. So we have to be always careful. It looks fancy, but the more the connecting points, it's a weak point. So calculation of fatigue for a lattice is a very impossible task, we can say that, because each lattice is a one connection and is a weak point. At every corner I have a weak point. It's very critical for a vibration. If I put a lattice into vibration, it will fail like anything. So these are the points we have to take into consideration. Where there is no rotating or load bearing, lattice is very good. But when it comes to load bearing point, we never say that use the lattice, because we have seen failure, and vibration is another challenge for any of this lattice or any unit cell. Vibration is a challenge. So we have to be careful, and this comes when we try with experience, it will come. This is another manifold which is already in space. We are allowed to show, but not the dimensions. So this is another example which we have done with Space Agency. So now this is again coming to the DOE analysis. Now we have too many variables. So my variables can be geometry, my variables can be support structure, my variable can be material. So how do we come up with the optimum process or material? So what we can do is we can run a AML algorithm, so or sensitivity analysis. So understanding that what is my each parameter affecting on the final part performance. So it can be residual stress, it can be microstructure. I think whatever we are discussing, it's already done. So what is the influence of each one on the final material property? So this one of the paper published by RMIT. So they have used our software and they have done all the microstructure validation. Yeah. So before that, we have to run through the conventional way of reducing the run order, sensitivity analysis. So it is more of a next version of statistical tool than sensitivity. So it is a new word given, but the base is same. It is a statistical tool where we use this optimization. And this paper is available in elsewhere as well. Yeah, this is a paper. The printing strategy, then reheating, and the microstructure. So all the correlation is already done with using the software as well as physical validation. So it is done at RMIT and available. So what they have done, so in fact a couple of team members were part of it. While printing, so how the subsequent layers are going for a heat treatment, So because of that, what is a grain change? So then grain, they are correlating into fatigue and creep. So if I have a finer grain and coarse grain, how my fatigue and creep life is varying. So for this kind of study, AAML is essential. Otherwise, you will have 200 and plus variables. How we cannot conduct, yeah.
Here you may get the tensile strength, but you may not get the required stability. There is an issue in this.
Okay, okay.
Because you are getting big grain, okay?
Mm.
If the grain is so high, you may not get stability.
Yeah.
Strength is possible.
Again, they have to change the grain size, vice versa. Yeah, that is, as I said, it's a DOE. There is no straightforward. So they have to run a DOE analysis and they will be able to do it. So this is one of the example which is already done. And now, we talk about only structural. What we missed is the manufacturing point of view. When we have a different printing strategy, how do we correlate that and other stuff? So how much time I have? Another 5-10 minutes? Okay. So how do we take that into consideration, like lack of fusion? See, my design is perfect, material is perfect, but I have a defect during process. So those things can be analyzed. See, all of this can be done physically, but if I say I have 200 variables, I cannot print 200 coupons or part. So that we used AAML to come up with a reduced run order. Then we print only that, rest will be done by the software. So that it will be, combination of software plus the physical printing, so that our prediction will be very accurate. So that is the overall idea. And we have a mesoscale simulation which can predict the lack of fusion defect. Also, it can say whether the chosen parameters are correct for a given material and whether it will fall under a stable zone or defect free zone, balling effect. So if I am doing more of a material related optimization, so that can be done over here. And a lot of development has been done on the aerospace and space point of view. So we closely, you name any global OEM, so we are closely working with them. Most of the modules were generated for a commercial. Later it is given to the public. So as I said, Nastron is a NASA structural code for a space application. It developed by NASA, then Hexagon purchased, made it commercialized. So like that, there are a lot of advancement happening where how we can use AAML for manufacturing. Once it is proven and once it has become patent free, then we will give it to the public. In the sense, all our customer can use that. So, and as I said, we are not only supporting from software point of view. We have something called Material Center, which is used by US Army for a testing, and all their data will be managed by us. If I have a 4 research business unit in the same organization, let's take Safran or GE. They have technical center in India, US, and let's say in Europe. So there will not be any repetition of the test done. So all of this will be uploaded over here, so that the colleagues can access any of the relevant test. It is done by within the organization. So those facilities also there. And what does it include? It includes machine information, any new material development, property related if I am working on a new material development, then the manufacturing related part detail, and what kind of process we followed. All of this will be available in the cloud-based platform within the organization. So yeah, so this is what we learned today. So I'm almost end of my presentation. So this is one of the drone startup in Bangalore. We have optimized for a drone. So this is a place for a battery and camera hold, and we have printed with SLA material as well as with FDM for a proof. And this is a bionic design for a medical implant and other stuff. This is a industrial application using DFAM. So all of this were a DFAM examples. Couple of other design which we have used. This is a wheel up which we are talking about. Other things, again, this two are wheel up. This is for a aerospace application, then application of tree root structure, satellite, and other application. So you can come up with any of this design, not only lattice, varying lattice plus solid and other stuff. One is applying lattice, but after applying, we have to ensure the durability and stress. In fact, we can do that. So if you have any further doubts, you can just write to me. So you can write to me or our global expert. So whatever we have seen is more of a industrial. So what we do for academic, I have a couple of slides for academic as well. So now we have come up with Sim Academy under Hexagon, where we do the certification, collaboration, and connect. The program is called. So this is already implemented in RMIT and many of A-Star University and other colleges. So where we run the program, so this structure is already available with us, or you can replicate the same what it is already done in RMIT and other stuff. So if you are interested, I will connect to the respective team, so who will be looking after this curriculum development and the software. So this is our development in industry, so which is already done at CMTI Digital Twin. The same part designed for a casting, machining, and 3D printing. So all of this, the same set of loading condition, but a different part which will be done with a different manufacturing process. And the inspection using robotics. So this is more of an industrial application where we create a digital twin reverse engineering for additive manufacturing process. So going forward, so you need not to use or install any of the software. So all of this will be available on the cloud, which is called Nexus. So all the tools and the data preparation software, everything will be on the cloud. Each students or faculty will be given with the login. You just have to log in and you open that software. No need to install, no compatibility issue, nothing. So everything will be on the cloud. So only challenges with the defense and government, they don't want to go for a cloud as of now because of the security purpose. But this is already available, and many are moving more of a subscription and cloud. Cloud credit will be there, so it will be some free credit. So after that, it has to be pay for usage. But for them to experience, it is easy to log in. They can log in as a Nexus, hexagon.nexus.com. If they can go, they can log in just to understand the workflow and what are the tools available. And third-party tools also now integrated with this platform. Yeah. So, and more importantly, so for our existing customer, we run something called a sixth sense. So where our existing customer need not to be the customer in the sense any user can come and present their idea. So let's say you have come up with your own unit cell design and you want to make it commercialize. So we have chosen one from IISc. So there is one professor has come up with one of the concept of, it's called EMI, the emission measurement index. When I have an electric component in the system, how much it is emitting for a surrounding component. So now we will be, Hexagon will be acquiring that concept, and we will fund to develop that concept. So patent discussion, other things will be discussed later based on the funding. So if you become customer, you have chance to participate in sixth sense. So whatever idea you have or any unique concept you have, so you can come and present. The rest will be funded, will be done by the Hexagon. So one we selected from battery range calculation. Another, which is this year there are two ideas selected from India. One from IISc, one from another professor. I don't remember, but the concept is on calculating the vehicle range. If I have a vehicle which is of let's say 600 kg, and if I have a 66 kilowatt battery, so what will be the range? He has come up with some equation and basic algorithm. So that will be funded by Hexagon to develop as a commercial tool. So like that we run this every year. So if you have any idea, just come register to Sixth Sense and you will get a chance to present, and it will be funded by us. And you have a lot of white paper case studies available in your website. If you are interested, just go through that. Yeah, so with this, I will end my presentation, and I thank you for your time. So if you have any questions I am open. Or you can write to me as well. I will just. Okay. It is there in the first slide, so you can write me. And it's already printed in the handbook. Yeah. Any questions?
So the software can be used as the artificial intelligence, right?
Yes.
Suppose if I am sending my original design to optimize, will the software able to identify whether the design has a scope to optimize or not optimization?
Yes.
Without the simulation, before that only it will identify.
So it will stop at one point saying that, so it's an iterative way. It will keep on running. So when the last iteration and next few iteration has seen no material reduction, it will stop saying that there is no scope for a further optimization. Now you can come back and do any modification. For example, you have not chosen the material. Now you choose the material. So then it will rerun. So like that. That is open.
One more is that apart from this generative design and topology optimization, this software can be able to identify like conformal cooling channel, part consolidation.
That is thermal management. That can be done. So it can be done because many heat exchanger were 3D printed. We have done. I have a live example with Bharat Forge. We have done that conformal cooling. So not only optimization, after printing, how do you ensure no powder is struck, no material struck inside a conformal cooling channel? That we have done it. I have case study. If you can, I can share that.
Sir, finally, which one is the better compared to subtractive and additive?
When the complexity is high, additive manufacturing. And complexity is simple, subtractive. So additive manufacturing, we say that it is not going to replace anything. It will be complementing, because complex design with conventional is difficult. So there additive plays major role. So it will be one of the substitute. It will not going to replace casting, machining, no. Because many 3D printed were machined for a better surface finish. Yes.
One education institution can